Okay, so welcome everyone to the next seminar of our spring series. And so today we have Hiro Nagataki, who is currently a chief scientist at RIKEN, at the Astrophysical Big Bang Laboratory. And Saji is also a collaborator of N3AS, and he is interested mainly in astrophysical explosive phenomena such as supernovae and gamma ray bursts. And obviously today he's gonna talk about about the supernovae explosions. So please, Hiro, go ahead.
Yeah, thank you very much for the introduction. Yes, I would like to talk about the evolution from supernova to supernova remnant. Okay, so this is a member list of Astrophysical Big Bang Laboratory, ABBL. And I'm PI and with staff member and postdocs and visiting scientist and alumni of ABBL. Yeah, ABBL laboratory. It's established about 10 years ago. And so many people left ABBL and get the next positions. So this is a time evolution of our laboratory members. And in this talk, let me call the current members as ABBL members, while alumni of ABBL as ABBL members. And I don't have time to introduce all of our activities, but yeah, people in red are contributing to this talk. And also, I have an affiliation at ITEMS, Interdisciplinary Theoretical and Mathematical Science Programs at RIKEN. He is a director of ITEMS, Tetsuo Hatsuda, nuclear physicist, and these are deputy directors. He's a mathematician, biologist. I am astrophysicist, and he is studying atmosphere and climate. And there are some astrophysicists in ITEMS, and the people in red are contributing to this talk. And today I'd like to talk about supernova and the supernova explosion and its remnant. So massive star, as you know, massive star explodes as supernova explosion. These are example of massive stars. This small point is sun. And you know that the stars maintains a hydrostatic equilibrium between gradient of pressure generated by nuclear reactions and self-gravity. But finally, the nuclear reactions has burned out. Then gravitational collapse happens at the final stage of its life. However, once gravitational collapse happens, proto-neutron star is formed. This is stiff due to the strong interaction between nucleons. So thanks to the stiffness of nuclei, gravitational collapse is stopped and the bounce happens. Then shock wave is formed. And this neutron star, proto-neutron star, is pretty hot, so neutrinos are coming out. This neutrino heats up the surrounding material, and due to the thermal pressure, explosion happens, and the neutron star is left. This is a rough sketch of the supernova explosion scenario. This is known by theoretical study, but for detailed study, supernova simulation is mandatory because the system is nonlinear, and a very expensive simulation is necessary. And these are ABBL members and ITEMS member who are doing very expensive numerical simulation of core collapse supernova, and they found that the successful explosion happens only for multi-dimensional simulation is done. So historically, due to the lack of computer power, one-dimensional spherically symmetric supernova simulation have been done, but all of the simulation showed the failure of explosion. I mean, gravitational collapse happens and the black hole is formed, and no explosion was found numerically. That was a long history of core collapse supernova simulation, but recently, thanks to the multi-D simulation and improvement of supercomputer, some successful models are being reported. And actually, observationally, supernova was neutrino event was detected by Kamiokande from supernova 87A, and 11 events were detected by Kamiokande at Kamioka in Japan. And he is Professor Koshiba, who received the Nobel Prize for the detection of the neutrino event from supernova 87A. Now, Kamiokande is upgraded to Super Kamiokande, so 50 K-ton of water Cherenkov detector with water Cherenkov detectors is working now. And if next supernova will happen in Milky Way, about 10,000 neutrino events will be detected. And the detailed comparison between simulations and observation will be done by neutrino detection. And now Hyper Kamiokande is under construction. So it's 260 K-ton, so pretty big. So next supernova in Milky Way or nearby galaxies such as LMC are hoped to happen for detailed comparison between simulations and observation. Also, supernova will emit gravitational waves, although the signal is pretty weak. So probably gravitational wave from core collapse supernova will be detected only if the supernova will happen in Milky Way. So this is, for example, time evolution of gravitational wave strength as a function of frequency. So this is well represented by the oscillation of proto-neutron star. So we can find the neutrino proto-neutron star oscillation by gravitational wave if the next supernova will happen in Milky Way in the near future. So future prospect for supernova study is something like this. More advanced multi-D supernova simulation will be done step by step. And the supernova event rate is about 1 per 100 year per galaxy. For example, last core collapse supernova in a Large Magellanic Cloud is supernova 87A, 35 years ago. And the last core collapse supernova event in Milky Way is Cassiopeia A, whose age is about 350 years ago. So once it will happen, detailed comparison of observations and the simulation will be done by neutrinos and gravitational waves, also photon observation. So such a comparison will tell us about supernova explosion mechanism, neutrino physics, gravitational waves, nucleosynthesis, equation of state. So this is very exciting event. The weak point, however, is that we don't know when it will happen. Maybe tomorrow, but maybe 10 years later, or maybe 100 years later, which we don't know. So from this, I would like to present about our unique approach on the study of the evolution from supernova to supernova remnants. So why supernova remnants? So currently, many supernova are observed by optical and infrared telescopes. However, they are so far, they are observed as point sources because they are happening in very far away galaxies. So they are too far to be observed by neutrinos or gravitational waves. So only by optical or infrared telescopes as point sources. So on the other hand, in Milky Way and local galaxies such as LMC, there are some young supernova remnants, and observations will tell us a detailed multi-dimensional morphology of supernova remnants. So we believe that the legacies of supernova explosion may be still imprinted in young supernova remnants. So this is an example of supernova remnants. 87A is seeing something like this, and Cassiopeia A, the youngest supernova remnant in Milky Way. This is a club pulsar and the club nebula, and W49b, the age is several thousand years old. There are some such young supernova remnants in Milky Way and nearby galaxies. So this reminds me of, about an analogy. So from, for example, T-Rex fossil to T-Rex. So, you know, this is fossils of T-Rex in New York Museum. And from this, we studied how it was when it was alive. So many people consider that the T-Rex is something like this, but Chris Pacman is saying that the T-Rex is something like this. But without any doubt, fossils of dinosaurs contain lots of information of dinosaurs themselves, of course. The problem is how accurately we understand dinosaurs from their fossils. This is an analogy from of the study from supernova remnants to understand supernova. This is our approach. So current status of study, our study is something like this. Unfortunately, lack of successful supernova explosion models, none. So strictly speaking, supernova simulation is doing well, but even for successful supernova explosion models, explosion energy is pretty weak. So about 10 times weaker than the actual observed supernova explosion. So in that sense, there is almost no successful supernova explosion models up to now. Supernova simulations follow the dynamics less than 1 second. So compared with supernova remnant age, the time scale is very different. So in future, of course, we would like to use successful self-consistent multi-D supernova models as our initial conditions. This is our future plan. However, currently, we mimic successful supernova explosion models in some ways mentioned later, which are used as initial conditions of supernova remnant simulations. And we did 3D dimensional hydro simulations that covered from supernova explosion phase to the supernova remnant phase. This is our unique approach. And as far as I know, this is the first supernova 3D simulation up to supernova remnant phase. Actually, such multi-D simulation with a large range of scales in time and length have never been done before, as far as I know. And but we could demonstrate that such simulations are really possible thanks to excellent international collaborations. Also, let me show you our study, and the example is 87A. First, we'd like to show you some observational hint from 87A. So this is a Large Magellanic Cloud. And if you see the Large Magellanic Cloud carefully, you see 87A. And this is the image of 87A, and the ejector is here. This should be a surrounding ring, which should have been formed before the explosion. And it happened in 87A in Large Magellanic Cloud. And it's the nearest supernova explosion observed by human eyes in hundreds of years, and a unique opportunity to watch a supernova change into supernova remnant. And this scale is something like this. So this is a supernova ejector. This is a surrounding ring, which should have been formed prior to explosion. And the progenitor star is observed, luckily. So this is a supernova explosion phase. But before that, a progenitor star was observed. And this is a blue supernova giant. And this is a very peculiar progenitor star, as far as I know. Not blue, not red supergiant, but blue supergiant. And a neutron star should have been formed at the collapse. But after that, neutron star is not found yet. What is the neutron star in 87A? This is a long-lasting problem for 87A. Also, interestingly, asymmetric velocity profile of iron is recorded just after the supernova explosion. And the redshift side intensity is high, while blue shifted side toward us, the intensity is weak. So this is not explained by the optical depth effect. If optical depth works well, so blue shifted side should be more intense than redshift side. But redshift side is really, there is a peak in the redshifted side. So this should represent the matter distribution, ion distribution, actual ion distribution. So this is confirmed by two wavelengths, and both of them are consistent with each other. So this should represent the matter distribution. So actually, much of iron is going to redshift side, and a small amount of iron is coming to blue shifted side. This signature is also found in titanium-44 decay lines, gamma rays. So blue shifted line, blue shifted side intensity is high than blue shifted side. So this is confirmed by two lines from the decay of titanium-44. And from this flux level, the amount of titanium-44 synthesized in 87A should be of the order of 10 to minus 4 solar mass. On the other hand, one-dimensional spherical symmetric theories predicted 10 to minus 5 solar mass for titanium-44. So there is one order of magnitude difference. And the bipolar explosion is seen in 87A. This is a time evolution of Hubble Space Telescope image for 87A. So in the beginning, the explosion is like a point source, but gradually it is expanding, and it shows a bipolar-like structure. So this is really a bipolar-like explosion. The evidence for that. Actually, such bipolar ejector is seen now by HST and VLT from the SI1 and FA2 lines, and the H alpha lines shows a bipolar-like explosion. But interestingly, the line of bipolar axis is tilted compared with the ring-like structure. This should have been formed prior to collapse due to the centrifugal force. So this should be corresponding to the equatorial plane of the progenitor star. But naively, I was expecting that this bipolar axis should be perpendicular to this equatorial plane. But in reality, this is tilted. This is interesting, but this is still an unsolved issue. And recently, ALMA observation, radio observation, told us the distribution of molecules in 87A. Molecules are formed in 87A now, and this is a distribution of CO in red, and green is SiO. So this is formed inside of the ejector region. And if you see carefully, a belt-like structure is seen, interestingly. for CO, and the SIO is inside of the CO. I'd like to come back to this issue later. And interestingly, a few years ago, Segan et al. Reported the warm region, hot spot in the ALMA observation band. So this cross corresponds to the center of the explosion. So the progenitor star exploded here, and Segan et al. Found that warm spot in the north region of the compared to the explosion site. So Segan et al. Discussed this warm blob may be coming from the heating by the neutron star. So neutron star may be hidden inside of the molecules and the dust, and the neutron star is heating up the molecules. So this warm region may be formed. If so, neutron star should be moving toward the north with 700 kilometers per second or something like this. In 35 years, if neutron star moves from here to here, the speed is about 700 kilometers per second. Okay, from now on, I would like to show you our theories for 87A. So I don't have time to explain in detail, but Takiwaki-san, ABBL member, did the 3D simulation with rotation. So rotation makes the dynamics asymmetric and something like this. And I'd like to skip the simulation because I don't have so much time, but he did many simulations. And for some case, he found that the bipolar-like explosion due to the rotation effect. And in bipolar-like explosion, about more than 20 years ago, I showed that a lot of titanium-44 is produced in bipolar-like explosion, because titanium-44 is produced by alpha-rich freeze-out, a combination between helium and calcium-40, and a lot of helium is produced by the high entropy in high entropy region, which is caused by the bipolar-like explosion. So in bipolar-like region, polar region, a lot of helium is produced and titanium-44 is produced. And the amount is 10 to minus 4 solar mass, which is consistent with observation of 87A. And the ABBL member, Anop Wong-Watanarat, did the asymmetric explosion and the neutron star kick. He did the 3D simulation of supernova, and he initiated a successful supernova explosion by assuming a spherically symmetric neutrino sphere on the surface of the protoneutron star. But even for such spherically symmetric case, asymmetric explosion happens spontaneously, and due to the asymmetric matter distribution, due to the gravitational attraction, neutron star kick is realized. So this is what he found in his numerical study. So due to the conservation of momentum, if most of nickel 56, this is a contour of nickel 56, that will become iron. If iron moves toward this direction, neutron star kick direction is opposite. There is an anti-correlation between the neutron star kick motion and the matter explosion direction of matter.
I think there is a question in the chat from George.
Just a quick question. So in that calculation you're just describing, what is the neutron star kick speed?
Okay, several hundred kilometers per second. So maximally, yeah, say 600 kilometers per second or something like that. 10,000, 1,000 kilometers per second is impossible.
But you get 600 kilometers per second, is that right?
Yes.
Okay, thank you.
Okay. Okay. And the asymmetry with respect to equatorial plane is suggested for 87A. So this is an asymmetric ion profile. And I discussed in 2000 that the asymmetric explosion with respect to equatorial plane is happening in 87A. And I demonstrated that such profile is explained. So thanks to Anup Natarat work in 2013, this picture is supported by his 3D simulations. So most of matter is going to red-shifted side. So neutron star should go to the blue-shifted side. This is our prediction. So blue-shifted side correspond to here. So this is correspond to the north region, and the red-shifted side correspond to the south region. So neutron star should be running towards the north region. This is our prediction. So let me introduce our advanced studies for 87A. So together with some international collaborators, they are solving the progenitor star evolution to reproduce the blue supergiant of 87A. And Masaomi Ono did the supernova simulation following this progenitor star evolution. Then Salvatore Orlando followed his simulation until the remnant phase. Then we could compare the our simulation result with observation of 87A. So I don't have so much time to explain the detail, but some people suggesting that these rings are formed prior to the explosion by the merging of binary star. So they are saying that the new 87A was a binary system and it merged before the explosion. Then these rings are formed. Then core collapse happened. So if such merging happens, progenitor star structure is really changed. And our collaborator took into account that effect, and then they solved the progenitor star evolution. Then Masaomi Ono did the bipolar-like explosion, assuming some explosion energy and asymmetry between the polar region and the equatorial plane, and the asymmetry between north side and the south side. So, and he did many simulations, and finally he found the best parameter to reproduce the 87A observation. So this is an example of our simulation. So this is a distribution of iron in 87A. So in polar region, lot of iron is produced. So this is an observed profile. So we don't pretend to reproduce everything. So there are several weak points, but anyway, roughly we could, the fitting is not so bad. Of course, for details, there are something that we could not reproduce. But anyway, most of matter is going to red-shifted side, and a small amount of iron is going to the north side. And this should be the neutron star side. Okay. Then this is the distribution of titanium-44. This is the observation of titanium-44. And the red-shifted component is dominant. And this is the observation. Black is observation, and with gray is the uncertainty of the due to the observation coming from the sensitivity of the new star observation. So gray is something observation, and the red is our theoretical model. So I don't want to say that we could reproduce everything, but roughly, at least our model is consistent with, not compatible with observation. And this is a structure of molecules. This is observation. And for simple treatment, we estimated the distribution of CO and SiO. This is just a multiply of C element and the O element. But anyway, due to the bipolar-like explosion, belt-like structure is seen in our simulation. This is our simulation. And the green is SiO. So this is inside of the CO. So anyway, belt-like structure is seen in our preferred model. So this is a merging binary model. Anyway, in future, for detailed comparison will be, we would like to do the detailed comparison between them. And this is our simulation for the evolution of X-ray luminosity. So X-ray luminosity profile is something like this by observation, by some observation. And the lines are calculated by our simulations. And initially, H2 region is the most emit most of X-rays, and gradually shock wave interact with this ring. And now the ring is emitting most of X-rays, but in the very near future, so ejector will emit most of X-rays, so which will be compared with future observation. And finally, our friend Emmanuel Greco found a hint of neutron star signal from Chandra and the new star data. So this is an observed spectrum. Without power law component, fitting is not so good, but they found that if we will add power law component for hard X-ray band with luminosity, something like this, fitting becomes good. So maybe this is a hint of neutron star from 87A. This is the first possible detection of the signal from the neutron star. And for the thermal component from the neutron star, when will we see the thermal emission from the neutron star? So our friend Akira Dohi calculate thermal emission, thermal X-ray light curves for many models. And this is the ALMA band. This is the upper limit of Chandra. This is a possible sensitivity by links. So Chandra is not so good to detect the theoretical curves, but ALMA is compatible with some his model. So maybe really ALMA hot blob maybe coming from the heating by the neutron star. And in future, if links will be launched, links sensitivity is so good, so maybe links will detect the neutron star signal. This is our prediction. Okay, I have run out of my time, so I don't have time to explain our other project for Cassiopeia A, but we already could demonstrate that detailed comparison between our simulation and observation is possible, even for Cassiopeia A and for type 1 supernova remnant. So I could demonstrate that such approach is really possible from the simulation of evolution from supernova phase to remnant phase and the detailed comparison with observation. So I hope you enjoyed my talk. I'd like to stop here. Thank you very much.
Yeah, thank you very much, Hiro, again. It was a very nice talk. So do we have any questions? Okay, I can see George.
Hi.
Thank you for a very nice talk. Very interesting. So I'm just wondering, the last model you talked about where there was a binary, involved in the initial model.
Yes.
And you did get a significant kick in that calculation, right?
Yes. Okay. Yes.
And I'm just wondering whether, so that kick that you got, is this the calculation by, yes, okay, this one. And I assume the kick was significant and in rough agreement with the new star result.
Okay, thank you very much. This is a good point, and yeah, Masaomi did many simulations to reproduce the 87A models, and asymmetry between the north side and the south side is controlled by alpha parameter, and he found that the alpha is about 1.5 is good to explain the iron profile and the titanium 44 profile. And due to this asymmetry, the neutron star kick velocity is estimated as 300 kilometers per second. So which is not so high. So compared with ALMA observation. So ALMA observation suggested 700 kilometers per second. So in that sense, not so completely consistent with each other, but this has some uncertainty. So they said that 700 kilometers plus minus 400 kilometers per second or something. So in that sense, roughly speaking, our simulation is consistent with the lower side of the kick velocity suggested.
Thank you. So my question really is that model that produced a 400 kilometer per second kick was a binary. Is that correct?
Okay. Actually, this is not connected directly. So we have not done such a binary simulation itself, but our friend took into account the effect of merger effectively. So they didn't do the multi-D simulation, but they did the 1D simulation. But they considered that some stripping of envelope should happen due to this merger. So for in 1D simulation, they stripped some envelope of the progenitor star, which makes a blue supernova, blue supergiant at the end of its life. Then, okay, well, anyway, they did the 1D simulation. So this kick is not coming from this binary merger. So this is a very interesting point, but currently we have not included such effect.
Okay, I'm just wondering if you can, if by using a binary, you could reduce the kick velocity.
Maybe or maybe not. Actually, I am pretty interested in this effect, binary effect. This corresponds to the orbit of the binary merger, and this axis should be related with the rotation of the core part. This is not aligned. This is my understanding, my guess. In future, I'd like to study such effect. So I'd like to show that this corresponds to the orbital plane between binary of the binary, while this bipolar axis corresponds to the rotation axis of the core, which is tilted. So this is what I want to study in future, but currently I have not done it yet.
Okay, thank you very much. Very, very interesting. It's sort of an open question how one gets any neutron stars left in, say, ultra faint dwarf galaxies where the escape velocity is very low, 2 orders of magnitude lower than what's observed in 87A.
Okay. Yes. Thank you.
Thank you.
Let me add one more word. So this corresponds to the north side. So correspond to north side from this with respect to the explosion side. This corresponds to the blue shifted side. In that sense, direction itself is consistent. And thank you. Thank you very much for your question.
Thanks. So next is Susan.
Oh, yes, I wanted to ask about the very slide, actually. In principle, I'd just like to try to put the apparent recoil blob velocity in broader context. I know that there have been quite a number of systems in which pulsar kick velocities have been measured. And I was wondering if you could just say a bit, isn't this actually rather faster than the typical pulsar kick velocities we measure? And do we understand why?
Okay, so I don't know that distribution of observed kick velocity of neutron stars, but Anop Wong Watanabe showed that this kind of simulation gives several hundred kilometers per second of the kick velocity typically. So as according to his conclusion, so this effect could reproduce the most of the observed kick velocity of the neutron star. That's my understanding. But observationally, there are some very high kick velocities, say more than 1,000 kilometers per second. Such very high kick velocity cannot be explained by this model. So something more would be necessary. So that's Anop's conclusion. And actually, as we discussed today, so maybe binary system may be working something more to push the neutron star a little bit more to explain the 1,000 kilometers per second, which we have not studied it yet, but this is what we are interested in.
Okay. Well, thank you very much.
Thank you.
Okay, thank you. Next question is from Youngzong.
Yeah, hi. I would like to revisit the issue regarding the two kind of observational signatures for this putative neutron star left over by the supernova 87A. So one is about this dust heating. You say that there were, studies showing that perhaps neutron star heating were responsible for the hotspot in dust part, right?
Yes.
And then there's also this fitting to the X-ray observation. You say that appears to be fitted better with a harder component from the neutron star emission. And my question is that, can you have some kind of a self-consistent modeling of these two observational hints for this putative neutron star?
Okay, yes, thank you. I'd like to move this. So actually, if ALMA is really explained by the thermal emission from the neutron star, so actually, Akira got some model to reproduce the ALMA luminosity. So X-rays are reprocessed to the radio band. Then some models are consistent with ALMA observation. And if we believe the Akira's model, so X-ray luminosity would be, yes, some order of something like this. So this is a sensitivity limit by links. So if ALMA blob is really explained by the neutron star model, so links should find the neutron star at this luminosity. This is our prediction.
The links, is that a radio observatory or is some
X-ray observation?
Real X-ray observation, all right.
And if links will not detect 87A, this is really challenging. So we need to reproduce the light curve, something like this. So some additional cooling effect, such superfluidity, very efficient superfluidity model must be introduced to explain both of ALMA and the links.
Okay, very good. This diagram answered some of the question, mostly towards the dust heating part. But there's this hint about the hard component in the X-ray. Currently, your collaborators fitted it to find that there is a better fit because there's this hard component from the neutron star. How does that square with this model?
Okay, yes. Oh, this is a thermal emission from the neutron star, and this is a Chandra sensitivity, which is much higher. So this Chandra component cannot be explained by the thermal emission. On the other hand, this hard X-ray component observed by new star, so this kind of hard X-ray cannot be explained by the thermal emission from the neutron star, but non-thermal emission, probably pulsar wind nebula is working and the particle acceleration is happening, and the relativistic electrons is emitting hard X-rays, which will be compatible with this hard X-ray observation. This is our picture.
Very good. But for those particle acceleration, etc., you require some magnetic fields and all those things, right?
Yes.
And can you infer what kind of magnetic field strength you require?
Yes, good question. I don't have number, but so this required luminosity is not so huge, and compared with other observed pulsar and the pulsar wind nebula, and the required luminosity is 10 to 30 something, 37 erg per second or something, which is not so huge, and very normal PP dot plane. The plot in PP dot plane is predicted if pulsar model in 87A explain this hard X-ray component. So normal neutron star can explain this luminosity.
Okay, thank you very much.
Okay, next question from Tianqi Zhao.
Hello, it's very nice talk. I have a naive question to ask you. Seems to ignore the asymmetry at the neutron star supernova simulation, but only include the asymmetry at the remnant simulation. Is that what's believed to happen?
Okay, thank you very much. What we neglected was the asymmetry in progenitor star evolution phase. So they did the 1D simulation for the progenitor star evolution phase, but Masaomi Ono did the 3D simulation for supernova explosion phase, and which was followed by Salvatore until remnant phase. So what I neglected is multi-D effect for the progenitor star evolution phase, which of course we'd like to include.
Oh.
Of course, the bottom line is that there is no successful supernova explosion model up to now. This is a very important bottleneck. So in future, I hope our collaborators will reproduce the successful supernova explosion by multi-D supernova simulation.
So could you explain a little bit when the kick acceleration finished in your simulation? Like
it is finished in a very short time scale, say the time scale of 1 second or a few seconds.
Okay.
Yeah.
Thank you.
Yeah, thank you. There's one more question from Sidu Lin.
Yeah, thank you for the very interesting talk. Let me ask a very maybe naive question. So here we show that this is a very interesting study about, for example, as you mentioned, a study for the dinosaur fossils. But and I guess except for that 1980 1987. Probably that's the only case that we observe both the complex supernovae and its remnants. And for most of the cases, probably we can only observe the remnants, and the explosion itself, we cannot observe it. So my question is that, so actually, what actually that we can learn from those remnants about the explosion before the remnants?
Okay, thank you. Thank you very much. Yeah, 87A is a very ideal target. But I believe that some comparison can be done even for some other remnants, such as Cassiopeia A. And this is our simulation. And so this is a 3D simulation. So supernova explosion model is calculated by Anop Wong Watanarat. He did many simulations, and among them, we found a very interesting result. Then Salvatore followed the dynamics up to 300 years old. And actually, this is an observation. And interestingly, this is iron blob in red. And inside a silicon layer. So this is very interesting. Iron should be formed inside innermost region, while silicon should be surrounding the iron core. But observationally, iron is outside and the silicon is inside. But this feature could be explained for the first time by our simulation. That this is not a good picture, but as a result of our simulation, this inverse is really happening in our simulation. So due to the very strong asymmetric explosion, so such strong blob is induced by strong neutrino heating, and the iron element penetrate the surrounding ejector. Then this inversion is really happening in our simulation and consistent with observation. So even though we don't know the explosion phase for Cassiopeia A, such a comparison can be done for some other young supernova remnants.
Okay, so if I understand correctly, so maybe what we are seeing is that probably some features of your supernovae remnants might be relating to the asymmetric supernovae explosion mechanism.
Yes.
So roughly. Okay.
Yes.
Thank you so much. Okay.
Especially, I believe that the young supernova remnant still contain information of the supernova explosion phase. Thank you.
Thanks.
Okay, so yeah, I think this was the last question. So thank you for all the questions and for all the answers. And so I think also our time is up. So let me thank you again for this very nice talk. And I'm looking forward to see everybody in 2 weeks again.
Thank you very much.
Thank you.
Thank you
Okay,
very much.
thanks.